Good afternoon, everyone, and welcome to today's webinar. My name is Chris Padilla, and I am the Training Manager with NDSU's Upper Great Plains Transportation Institute. Today's presentation is being hosted by the Transportation Learning Network, or TLN. TLN is a program within Upper Great Plains Transportation Institute at North Dakota State University. For more information about UGPTI and our programs, go to our website at www.ugpti.org. At the webinar today, the presenter is the only one that has the ability to project audio over the webinar, so please be sure to ask your questions using the chat box below the presentation. Also ensure that your computer speakers are turned up so that you can hear the presentation. There is not a conference call-in number for this event. This session is being recorded. Should you want to review a part or all of the presentation again, you may log into the Learning Management System where you registered for this presentation in about a week, and the presentation will be available. At that point in time, the PowerPoint presentation will also be available for download. Now on to our topic and speaker. Our topic today is titled Use of Travel Time Reliability, and Winter Condition Index Information for Improved Operation of Rural Interstates. Our presenter is Dr. Rhonda Young. Dr. Young is an adjunct professor with the University of Wyoming and an associate professor at Gonzaga University. Dr. Young earned her undergraduate degree from Oregon State University and her graduate degrees from the University of Washington. As a professional engineer in Wyoming and Washington, she specializes in the operational side of transportation engineering. Her research interests are using technology on our roads to make better operating decisions and truck blowovers, looking at the wind effects on trucks. With that, I'm going to turn the presentation over to Dr. Young, and she may begin.
Thank you. So it seems like the appropriate time to start talking about winter, right? It's coming any moment. I heard, I'm now in Spokane, but I did hear that they got snow a couple of weekends ago. So anyway, I'm currently at the Gonzaga University, but I maintain adjunct status at University of Wyoming, where I was at for 13 years. But I want to make sure as we move into the presentation, see if I can control the slides. Doesn't look like I have
Dr. Young?
the ability to move the slides yet. Anyway, while we get that worked out, I want to make sure that I give credit to Eric Milliken, who was the graduate student on this work, and he is currently at the City of Laramie, so kind of waiting for Chris to give me permission to move the slides. There we go. Sorry about that. Anyway, and then you can see Eric's name there. And as I said, I forgot to update. He was formerly at Dow, but now at the City of Laramie. So our presentation today will focus mostly on the research work that was Eric's graduate thesis. And so the bulk of it will be kind of going through the background, methodology, and the results. And then at the end, there's a couple updates on what has been happening recently on the I-80 corridor in Wyoming and some other research on travel time reliability. Okay, so this work, the idea for this research project came back in 2008 from some earlier work where we were looking at the dynamic message signs between Laramie and Cheyenne. And we had gathered focus groups of both regular and random travelers, so travelers that we had intercepted at the rest areas and travel plazas, and had asked them about the reported conditions that they experienced on their trip and the information that they received both pre-trip and during the trip about the conditions. And what we found from then was that they really responded, obviously, to road closed, that they couldn't go through the corridor, but also the no unnecessary travel. But beyond that, any other conditions that were reported, they weren't really taken as seriously, and there were also concerns that they weren't updated as quickly as desired. I do want to point out this was back in 2008 and that there's been considerable change at the TMC, and I think that you would probably get different results now. But regardless, that information about, the inability to really discern whether it was a minor condition or sort of a moderate condition, that they were only responding to the most severe conditions. And It could be the intrepid spirit of people in Wyoming, but it also was just, how do we convey different conditions and sort of the gradation of conditions. So that led to the overall research question of the project that I'm going to be talking about today, and it was whether we could utilize ITS technology, so any kind of sensors out there, to create condition reporting system that could update more frequently, but also better convey the range of possible conditions. So something beyond, ideal and no unnecessary travel. So just a little bit of background or literature review. As I mentioned earlier, that work in 2008, but there was also work done by another master's student, Paul Ringerberg, in 2011, where he was looking at some of the DMS messaging sign along the corridors too. But also, as kind of a subtopic with that, is he started looking at whether speed sensors, so the external Wavetronics radar sensors, could be used to measure travel times. So could we build up the speed observations we were seeing into overall travel times? From that work, we kind of looked at a data set and looked at what we thought the ideal density of speed sensors. We happened to be working on a corridor that had a lot of speed radar sensors, so we had lots of observations, but we also kind of looked at what happened as we kind of used fewer and fewer sensors to see where kind of the cutoff was. This becomes important as we talk about rural travel times, just because we're dealing with large distances, often remote and expensive to get crews out there to do calibration or maintenance on those, as well as just the initial capital cost for those. So from his work, it was determined that the ideal speed sensor density was 10 miles per 10 miles per sensor, which is still pretty close together when you're talking about rural areas. So. Some other things we looked at is, well, how are travel time calculations done? Looking at previous literature, they really fall under kind of two categories. One is a pilot car method, where it's a single car, a single driver representing, the overall travel times of that corridor. Kind of more common probably in the literature now is floating car method, where you have a series of observations, either fleet vehicles, citizen reporting, and or using technology. So some of the technology ways are using toll transponders, even outside of toll facilities. If those transponders are constantly sending signals, you can use those. That's something that's used quite a bit by Colorado DOT, so they're doing that in the mountain passes. So the toll transponders may be associated with the toll roads around the airport, but so many people, they have a fairly good representation of travelers, so they're able to use that. You can also use license plate matching. Everybody is required to broadcast their license plate. That does have some privacy concerns. That seems to make people a little bit more uncomfortable than some of the other methods. And then the last one is the one we're going to talk about, where we use our MAC address. And the next slide will have a little bit more on that. So a lot of devices, so technology that we have in our car, whether it's working with different devices speaking to each other, have a unique MAC address. It's a 12-character code. The first half of it is related to the manufacturer, and the second half is unique. And it's usually assigned at the time of manufacturing, and it's something that is unique, but it's not identifiable, meaning that there's no sort of database out there of people's MAC addresses. So it's something that your device is transmitting when it connects to outside networks, so we can use that. And if we can see that MAC address at multiple locations, then we can get travel time information from that. So kind of continuing on, so this Bluetooth sensor, which is picking up the MAC address at different locations, is something that had been researched quite a bit in urban areas. Most of the previous research we found when we were doing our project focused on pretty relatively short corridors, particularly compared to what we were thinking about in Wyoming. When we looked at the travel times, the research on the travel times from the Bluetooth sensors compared to pilot car testing, it found that there was no significant difference, meaning that the Bluetooth sensors were providing the same information as what was viewed as sort of ground truth, or the real number. The problem with Bluetooth is that early modes of cell phone devices, you transmitted that Bluetooth MAC address all the time. Most modern cell phones now, you have to be in discoverable mode. So at the beginning, like when you're pairing with your car or your headphones or something, you move your phone into discoverable mode. But once the pairing is done, you don't broadcast your signal in the same way, and so the Bluetooth sensors have a harder time picking up on that. So now on with the corridors that were part of this research. The first corridor, or the main part, was between Cheyenne and Laramie. So down in the southeastern portion of the state, we were looking at milepost 317, which happens to be right in Laramie, over to milepost 358, which is just outside of Cheyenne. Through this part, through this milepost, the interstate is a divided 4-lane, so 2 lanes in each direction, except for a short climbing lane in the eastbound direction at milepost 318 to 324. It's a heavily instrumented corridor. It's been subject to some major sort of technology investments. So there's 14 speed sensors, there's 3 weather stations, lots of webcams, and dynamic message signs, and it's also currently under variable speed limit control. So there's 20 variable speed limit signs out there. So the speed sensor mileposts you can see here. You can see how they're distributed, and they're in some cases they're quite close to each other, and then in other cases you see some separation between them. The corridor is pretty high in elevation. All of it is above 6,000 feet, and it tops out about 8,000 feet, so weather is certainly a concern. The other corridor we looked at was Wyoming 28, which is more in the central part of Washington, or the west central. So this is a considerably different type of roadway than the interstate. It goes between the towns of Farson and Lander over South Pass in the Wind River Range. So it's a rural 2-lane highway. It has a section, 3 sections, I believe, of climbing locations. You can see the milepost there, but there's 1 in the eastbound direction, and there's 2 in the westbound direction. Generally higher, Farson is higher in elevation than in Lander, so your net gain is higher in the westbound direction than it is in the eastbound direction. It's also an area with variable speed limit control, and because of that it has pretty significant ITS technology. It has speed sensors, weather stations, webcams, dynamic message signs, and the variable speed limit. The ADT on this corridor is about 1,600 vehicles per day, and I should have pointed out that the ADT on I-80 is around 15 to 16,000, and with about 45% of that trucks, so pretty significant cross-country truck travel. This road on Wyoming 28, at the time of our research, was really the traffic volumes were being driven by oil and gas exploration and development in different corridors. So it was getting some heavy truck traffic, but a lot of sort of oil and gas field worker kind of commuter traffic. So just a little bit of background on the pre-trip information sources, so where people are currently getting their travel before they make their trip. So Wyoming has a really active website called wyoroad.info. I heard just the other day that they had their biggest year where they were approaching, I think, 1 billion hits per year. At the time we were doing the research, I think when we looked it up, it was getting about 600,000 hits per year. There's also the 511 telephone system, which I looked up numbers during the time of this research, was getting about 1.9 million calls. And the 511 notify system, which is similar, but instead of telephone calls that you call in, you're either getting automatic text or email messages. So I think during the time last I looked, it was about 36 million text and email messages per year were being sent out. So the dynamic message signs that I mentioned in both of the corridors, these happen to be pictures from both of them from the I-80 section, but they're consist of both side-mounted and overhead-mounted and either 2 or 3 line DMSs. So the data. So the speed sensor data, so all the speed sensors along the corridor are Wavetronic smart sensors, which provide through radar direction of travel, the length of the vehicle, the number of lanes. A single sensor can read multiple lanes of traffic and self-delineates those traffic. I think, according to their literature, can do 22 lanes of from a single sensor. But so each sensor can read both directions, headway and lane occupancy. So the data for the speed sensors for this research was collected between October 2009 and 2010, so a full year of speed sensors. The way the data is currently goes into the TMC, they're aggregated, so you're looking at 15-minute average intervals, and so the total data that we looked at was over 1.4 million records from all the speed sensors for all those time periods. The speed sensor data on Wyoming 28 was kind of slightly different because the ITS was installed on the corridor in October of 2012 and started collecting data on November 8th of that year. The speed sensors were set to download for 1-minute averages, but those were later in the office converted to 15-minute averages so that they were the same time period or aggregation level as the I-80 data. So we had less data to work with because of when it was installed and when we were doing the research. So we were dealing with data only from November 8th to January 27th. This will kind of come up again that it was just primarily during winter seasons that we were analyzing. And then we later went back and recorded individual data. So instead of looking at aggregated speeds, we looked at just the every vehicle was a single event in the data. And we did that for a series of storms that happened between March 9th and March 28th of 2013. So in addition to the traditional or the ITS devices that were already installed on these corridors, we looked at installing some BlueCompass devices. So these are devices by Acyclica. We looked at a couple of different manufacturers, but these ones were local. So they have an internal antenna that can read signals up to 100 meters, but we installed these in cabinets and also installed an external antenna to make sure that we were getting good radius to read from. It can store up to 5 gigabytes of data, and then you can manually download them. They can also be outfitted to transmit that, but for this research we were just downloading them onto a laptop or bringing them back to the office, and we were installing them in existing ITS cabinets out on the corridors. It has a web-based interface, right, and IP addresses, and everything comes in comma-separated values that we could then analyze. And this is just a sample of the data. So you see a timestamp, a MAC address, and the sensor that it's being downloaded. So if you have multiple ones, you can then use a matching process, right? And if you see that MAC address at multiple locations and you know the mileposts at each one, right, you can back calculate and do the travel time. So just a little bit about what we found using these devices out on I-80. And this becomes kind of important because we were hoped to have good number of observations and that these Bluetooth sensors would be able to replace the speed sensors so that we would, instead of having devices, speed sensors every 10 miles, that we could have one at the beginning and end of corridors and through the matching of these MAC addresses. But as you can see on this chart, when we looked at this is just an observation over 10 days, you can see that we were getting 76 hits per day. And remember, this is on a corridor that has an average daily traffic of about 15,000. So we're getting a little over 3 hits per hour. And when we looked at the speed sensor data for the same period, we were seeing that we were getting less than 1% of the vehicles being able to be matched in multiple locations with this. And then, interestingly, down below also shows the hits by time of day. So it kind of shows you that it's very much not a commuter corridor. I mean, you get some commuter traffic between Laramie and Cheyenne and people working in different cities, but really this is a corridor that's very rural in nature and driven by freight traffic, so you don't see as much of the sort of morning and afternoon peaking that you would in an urban setting. But still, the big takeaway from this is it's very little or relatively low number of hits per hour. And so if you're going to be basing travel time information on, just 3 observations per hour, there's some concerns with the reliability of that data. We also wanted to link it back to weather, so we downloaded data from the main RWIS station, which happens to be at Vedauwoo, which is sort of midpoint in the corridor. And we pulled that data from October 2009 through December 2009. Every RWIS has slightly different sensor packages and some reliability issues with the weather, but I'll kind of come back to the analysis that was done with the weather later. But in general, you get air temperature, wind speeds, surface condition, precipitation, and then also relative humidity. So the methodology and results that was done with all these data sources. So the first one was just doing the speed sensor travel time analysis. So looking at that year's worth of data, right? One sensor was chosen as the starting sensor, and average travel times to the next sensor were calculated just using the average speed from the beginning sensor. So if you're talking about 15-minute average speeds, you assume that every vehicle, right, is traveling at that average speed, and then the distance between them, so you convert that into a travel time. So we used the 10-mile density rule that was done from the earlier research to pick out which sensors would be part of this travel time analysis. And at the speed limit, which is set at 75 miles per hour, except for a portion of the corridor which is going through Telephone Canyon and has the climbing lanes, which is set at 60. But considering this, the travel time is 34 minutes. So for those of you familiar with the corridor, you'll recognize that's a pretty short travel time, but we're going from not from downtown Laramie to downtown Cheyenne, but kind of from outskirts to outskirts. So that's why that travel time seems a little bit short. So this is the data of what the travel time analysis for that 1 year looks like. So this is a probability density function. So when you look at travel time research, most of the research for different corridors comes back to a probability density function. So what did the distribution of travel times look like in that corridor? And you can see some things that might look familiar if you've looked at other research, and some things that look kind of strange. But as you would expect, things would be sort of built around an average. So if you remember that the sort of ideal, or everybody traveling the speed limit, would be around 34 miles per hour. So, but in this corridor we get bimodal distribution, meaning we have two strong peaks sort of below and above the average, and then we have a long tail showing the different travel times throughout that entire year, which would have had one winter season from it. So the long tail of high travel times is pretty common in probability density functions for travel time, but the bimodal part is a little bit unique that I'll come back to in a second. I do want to point out that all of this was done when the roads were open. One of the confounding factors of this corridor is what happens when you introduce travel time distributions to a corridor that can have complete road closures. And if you are familiar with IAD, you'll know that in winter months, or actually any time of the year, but mostly in winter months, you can get road closures quite frequently. There's several dozen per year, and some earlier research that we did, the average duration of those closures is 8 hours. So you could get really, really sort of another tail way out there where you have kind of infinite travel times, or essentially 8-hour or multiple day travel times due to the closure of it. For this research, we didn't include anything during road closure times. So westbound, it's still bimodal, but a little less pronounced. You can still see those two. So one of the questions came, well, where did that, why such a strong bimodal distribution? It could have been between night and daytime driving, right? Because we're doing this 24 hours a day, and as you saw, we have, pretty steady traffic relatively throughout the day. Well, as shown by the Bluetooth sensor data I showed you earlier, because of being a major freight corridor, you do still get kind of traffic all the time. So we looked at that using nautical twilight as a reference point. We looked to see if that was driving the bimodal distribution, but that's something that you would see in pretty much every corridor. The bigger one was thinking about the percentage of trucks. It averages 45% trucks on a year-long basis, but during sort of winter weather when the tourist travel is lower, that percentage can creep up, even as high as 60 or 70%. So this is looking at speed distributions if we broke it up into cars and trucks. So this was at another point along I-80 where we're looking at speed data, and you can see the distribution by car and the distribution by trucks. And combining that same observation, you get the bimodal distribution. So that's what was causing the bimodal distributions we were seeing. So we also did something similar looking at the Wyoming 28 travel time analysis. So we had different data periods we were looking at. Same methodology as the I-80 travel time analysis, but we had a lower speed limit of 65 and a longer expected travel time, so longer distance between them of 69 minutes. So we get a more typical travel time frequency distribution for this roadway. There are trucks on the road, but not to the extent that you see on I-80 from a percentage basis. So you can see the single mode. And the long tail out to the edge. So this is in the eastbound direction. And you can also see on the westbound direction where we're getting more grade effects. You have more net elevation gain as you move from the westbound direction from the eastbound direction to the westbound direction. So we start to see the effects of the trucks on the corridor a little bit more pronounced. One of the things that this analysis showed was the average travel time that we got from our analysis was much longer than we expected when we compared it to ideal conditions. And so you can see for both the eastbound and the westbound, you see the average travel time of 75 minutes and then the 95th percentile. But the interesting one is the last row on that, which is the standard deviation, showing on the eastbound over 10 miles per hour standard deviation for our travel times, and on the westbound approaching 15 miles per hour. And what this told us is that we didn't have enough ideal condition data, that since we were only looking at a time period in the winter months, the data was sort of more proportionately skewed towards having winter weather. And so if we were to look at a full year event like we did in the I-80, you would expect to see those standard deviations much lower, and you would see the average travel time be influenced more by ideal conditions, and so you would see it lowered, be closer to the sort of 69 that we would have expected. So it's an interesting thing to look at, but if you only take observations in the winter and try to make probability density functions from that, you're going to weight those non-ideal conditions a little bit too heavily. Some other things about the travel time statistics between the different Bluetooth sensors. So this is back up on I-80, and there was a Bluetooth device at milepost 317, which is in Laramie, up further to the east at 334, and then the final one was at 343. And so this showed that the travel times and the standard deviations of travel times based on the Bluetooth devices as opposed to the speed sensor devices that we saw before. The averages seem reasonable, and the standard deviations are a little bit lower. Through the analysis, we also then did statistical tests to say, were the Bluetooth sensors giving us the same distributions that we would have gotten had we calculated from the speed sensors? So remember that the research question is saying, can we use these Bluetooth sensors instead of speed sensors in order to sort of save on infrastructure costs? And what this statistical test does is it just looks at the data or the distribution of the two different data sets and asks whether they're similar. Not to get too much into the statistics we're showing, but you can see from just the first line with the mean, the Bluetooth had a much higher travel time than the speed sensor data on both the eastbound and the westbound direction. We also had higher variance. Remember, because the Bluetooth sensors, we had many fewer observations. The speed sensors, we had lots and lots of observations, and so you would start to expect that variance to go down. It's based on lots of observations within that time period. So even though they both were looking at 64 time periods or 71 time periods, depending on westbound and eastbound, there were more observations within those time periods, which is why you see the sort of dampening of the variance between them. But even just looking at those means, you would expect to see that the statistical test wouldn't have shown that they were the same. And in fact, it did. It rejected the hypothesis that they were the same, so that they were giving us different results. One of the things that we thought about, or trying to figure out, well, why would the Bluetooth sensors, why would the data that we were getting from those have such a higher travel time than ones we were getting with the speed sensors? And one of the hypotheses, was that we were picking up more freight trucks, that they're, the way modern sort of freight logistics and modern freight or truck drivers, that they just have more technology in their trucks, maybe. That was what we were guessing, and that they were more likely to pick up on their devices in their car than the vehicles. And then since the freight trucks were going slower, that we would get slower travel times. But there's no way to test that theory other than the fact that something was statistically significantly different and slower from the Bluetooth observations than the speed sensor observations. So one of the things is, if we ultimately are trying to get back to how do we operate corridors so that we give better information to the public so they can know what the conditions are currently like. So if you only have dynamic message signs or pre-trip information that's talking about the whole corridor, how can we convey, in general, is it just, a small section of the road, maybe slippery in spots, or is it the entire road is icy? And the idea of travel times is that it conveys to the user their entire trip. And so the hope was that we could create a travel time index. So based on what typical travel was on that corridor, how do we convey that? Well, one of the issues, most of the times when you see travel times, you see them in urban areas. And you can say, the travel time between junction A and junction B is X number of minutes. And that works really well for people who are commuter travelers. And so they know how long it typically takes them. And so when you tell them that information, they have a baseline to compare it with. We were concerned on I-80 in particular that we had a lot of travelers who didn't understand how long it would normally take them to go from Laramie to Cheyenne. And so if we were to put up a sign or to give information that said, okay, the current travel time is X number of minutes, if they didn't have a baseline to go from, that was, it wasn't very useful information. So the idea of creating a travel time index or a gradation between sort of normal, ideal conditions and severe conditions, that could be better understood by travelers who may not have the familiarity of the travel time. So this travel time index was a way of taking that distribution curve that we had and breaking it down into sort of levels. So what this slide is showing, on that chart is that green would be ideal. So the travel time was less than 40 minutes. Everybody was traveling sort of at near the speed limit, right? Or the average person, right, would be able to travel it on that. But then to look at where the other breakdown as we go from green to red and kind of thinking about five or these six categories as different levels between it, we actually found that there were sort of slight peaks in the data at 70 minutes and 100 minutes, meaning that there were sort of clusters of travel time frequencies that we observed at those. So we knew that we wanted to use those at least as two of the thresholds. And so you'll see that 70 was used as a threshold between the purple and yellow, or category or index 2 and 3. And then the 100 was used to differentiate the orange and the red. So that was some of the decisions that led to this index. So what we did with that was we created a flow chart, meaning how the methodology that could be sort of programmed into TMC operations using this travel time data and those thresholds. And then we also applied that index to a year's worth of data to see what would have happened had that system been in place. How many hours or how frequently would the different indices have been reported in that past year. And so this is what we're seeing in this chart, which is for the westbound direction. So you can see that for index 0, which was sort of ideal conditions, for that year, remembering it's winter and summer, it was just under 70% of the time. So if you have indices, right, you want to make sure that they're picking up on sort of differences of condition, but also not being reported so frequently that they just become sort of, old news. So if you see, as we move to index 1, which was the sort of not ideal conditions, but representing some sort of weather condition out there, you see that it's 10% of the time, and then on down the frequency gets lower, down to level 5, which is almost 0.2% of the time. The average duration shows that once that index was in place, on average, how long would that condition have been reporting? So for index 1, where we had it up 10% at the time for that simulated 1-year period, on average, when condition 1 was shown, or index 1 was shown, it was shown for almost 3.5 hours. So interesting to note that there is fairly common or fairly similar results for sort of 2 through 5, both in the average duration and a little bit in the percentage of time. So eastbound results just show pretty similar. We get a slightly higher percentage of time under index 0 with 72% compared to the westbound direction, but still relatively similar results both in the percentage of time and the average duration. So the other task that was done, or the final task that was done with this research, was to look at whether we could compare the travel time index that we generated through that 1 year's worth of data versus weather variables. Because in addition to reporting travel times, when you're talking about rural corridors where the travel time distances are fairly significant, but also people, have to make plans for making these trips, or, once they're out there, they may be concerned that the travel time index or the conditions would change, and, there's relatively few services along the way. So could we predict, right? So could we link the travel time to weather variables both observed, and ideally, if you got a strong model, could you then forecast travel time indices based on forecasted weather? So the analysis method was to look at the travel time index and also the weather from the roadside RWIS station to see if a strong sort of model could be done. Since we're modeling the indices, which varied from 0 to 6, this is considered categorical data that's also ordinal, meaning that the number has magnitude to it that means something. So an ordinal logistic regression was selected. When you're talking about weather variables, correlation becomes a sort of statistical problem because you have a lot of weather variables that essentially are telling you the same thing or too similar thing that it'll cause sort of modeling problems with it. So if you look at this chart, there's three sets of variables where these issues were identified through what we call a correlation index. And so the first one is air temperature and surface temperature. Obviously, surface temperature is impacted by air temperature, so we see very high correlation. The closer to 1, the more sort of correlated they are. The same thing with gust wind speed and average wind speed. So, you have high gusts at the same time as you have high wind, which makes sense. And the other is precipitation and relative humidity, right? You're more likely to have high humidity when it's raining, which is intuitive or by definition almost. So because of that, you can't have for the first one, air temperature and surface temperature, it's telling you that you're going to have modeling problems if you have both of those. So you have to make a decision as a modeler about which one is more important to you, but your model shouldn't be specified with both. So in all three of these cases, one of the variables had to be removed from the model. So kind of limiting the overall number of weather variables available for modeling. So anyway, run through this statistical package, right, and we can get information about it. The intercepts for the 5 different indices, the base condition would have been index 0, which is why it doesn't have an intercept value to it. But the big thing here is that it really only left air temperature, relative humidity, and then another binary variable which just said whether it was day or night. So when you're looking at this as a good model for weather prediction of travel time indices, just given the relative few modeling or weather variables left in the model, it has pretty low potential for being useful as a predictive model. So anyway, so the last part of it is if moving forward to go, what would be the implementation method? How would this information be given to the public? So if you look at dynamic message signs, there's a lot of federal highway guidance on how dynamic message sign messages should be constructed. They should be short and as concise as possible. When you look at interstate speeds or any speeds greater than 35 miles per hour, there should be no more than 2 lines per phase and no more than 2 phases. So this is just some ideas about the travel time. So going back to what I was saying before is that commuters might have a baseline at which to take a travel time number and compare it to get an idea. It's also important to convey maybe just the average speed so that you wouldn't have to have that baseline. So what was proposed was a 2-phase DMS, one having the travel time, right, and the other having average speed. Right. For the pre-trip information source, using those color codings of the different indices, the existing maps, travel time, or the existing pre-trip information maps that Whiteout uses, there could be another layer that had travel index on it, and then that could be conveyed by color. And not right now it's just showing for the purple for the research corridor, but it could be for the entire I-80 corridor, and done using the same sort of methodology with both the color coding and also the travel time information, both the travel time and the average travel speed. So that kind of is the end of the research that was done for this project. But I wanted to just update on what happened between the end of the project and what's currently going on I-80 corridor. So right now the focus of operations on the I-80 corridor has switched to the use of connected vehicle technology. So that corridor, the entire I-80 corridor, was selected this time last year, by the USDOT as one of the 3 connected vehicle pilot deployment sites, along with New York and Tampa. So Phase 1 recently wrapped up, and Phase 1 was all the system design. So all the preliminary deployment information and system architecture, system readiness, all of those tasks were completed, and as of September 1st, 2016, we've moved into phase 2, the deployment. So this winter we'll be, putting roadside devices out, instrumenting vehicles. This winter is a pretty important winter for us for deployment, and then we'll move on into system demonstration. So the idea of using connected vehicle data and possibly in similar ways to what was talked about with the Bluetooth or the speed sensor data might provide lots of opportunities for continuing with travel time research. But if you're interested in what's happening with the connected vehicle, there's a whole USDOT website under the pilots, and there's, I think, 12 different reports that were done for phase 1. So it's kind of an exciting time on the corridor. And then the last piece that I would put out, this is something I've been following with travel time reliability. It was a major topic. It was one of 4 major topics, is the SHRP2 projects. So the reliability, SHRP2 reliability projects. There was a research program. Like I said, it's one of the 4 areas that SHRP2 research funded, and there's just a tremendous amount of work being done in travel time reliability, and so there's whole websites based on that. I would say, kind of keeping up with travel time reliability, I would say that there's still really a strong urban focus. There are pieces within the research, if you go to this website, that will have some applicability to the rural area, but I'd say that it's still a challenging one, both in how to get the appropriate technology out there and how to convey it to maybe non-familiar travelers who have long decision points. And so I guess I'd say that there's lots of work that have been done, but there's still some outstanding questions that are pressing, I guess. So I have faith in, maybe connected vehicles and just the data that it's going to provide. We'll be able to get some, quality information out. So with that, I would say I don't see if you have questions. I'll pass it off to Chris here, but I would say if you wanted to email me, here's my contact information. Both my previous at University of Wyoming and my Gonzaga emails are both active. And then Eric, the graduate student who did the vast majority of this work, here's his contact information at the City of Laramie. So I'll pass it back to Chris.
All right, thank you, Rhonda. Great presentation. Thank you, everybody, for attending. If you have any questions, please do type your questions at the bottom. We will hang tight for, say, the next 2 to 5 minutes. Please do not leave the webinar. When we end the session, you'll be prompted to complete a survey. And at that time, if you would, please conduct that survey, complete it so that we can get good feedback on the presentation so we can make changes and improvements to our future presentations as we move forward. Again, we'll just kind of sit tight here for a couple minutes, and if there are no questions, again, thank you for attending. This session will be available within a week on the Learning Management System should you want to watch all of it or parts of it again. And thank you again, Dr. Young, for your presentation. Rhonda, do you see that question there?
Yes.
Okay.
I was typing it, and then I realized I could actually talk.
Yes.
So I guess I understand this question. So GPS, probably from fleet vehicles, that would be the only access. I know that some people have used cell phone data and the GPS-based data that can come from that. At the time, that wasn't something that was readily available, and the only GPS that we had available was from fleet vehicles, and we were concerned that they weren't, like the highway patrol or maybe the snowplows, and that those wouldn't be as representative of true travel times because they'd, likely be traveling sort of faster or slower because of their duties. So I would guess that we looked into it a little bit, but what we had available at the time. I have read quite a bit of research that people are buying the data from the cell phone companies and finding that. I haven't seen any in rural areas, and I'd be pretty interested to see if it's good enough representation. Okay, so about the weather information, we didn't find that it was our indices as we had created them were not able to be predicted by weather, just we weren't able to, I guess, model a good prediction one, model from it. We didn't use forecast. That was one of the thoughts at the time. We only used RWIS data, but we did have, we were getting forecasted data from, I believe outside of Utah, that they use for maintenance purposes, and we've used that data for some other modeling, dealing with some safety issues on variable speed limits and whatnot. It would be interesting to do to see if the forecast data was a better predictor. But all we did was use the RWIS and linked it to our indices. So.
Okay, not seeing any other questions coming in. On behalf of NDSU, Upper Great Plains Transportation Institute, Transportation Learning Network, and the Mountain Plains Consortium, thank you for attending.